Hey, welcome. Today, we're diving into a story about how you solve problems that seem, well, completely unsolvable. We're talking about a kind of universal recipe for discovery that can handle everything from the quantum weirdness of black holes to climate change solutions right here on Earth. So, how can one recipe possibly solve it all? Let's get into it.
So here's the big question, right? What happens when the science you're trying to figure out is so complicated, so out there, that the equations we normally rely on just stop working? You literally can't write a formula for it. How do you even begin to find an answer?
And a perfect example of this is the ultra-spinning Myers-Perry black hole. Now, these are not your regular everyday black holes. They exist in higher dimensions, and they spin so incredibly fast that they just push the known limits of physics. Trying to understand them is what scientists call analytically intractable, which, is really just a fancy way of saying the math is so hard it's pretty much impossible to solve directly. And this is where our hero enters the story, the Myers-Perry-Pajo framework, or what we're going to call the MPP recipe. Now, I want you to think of this not as just a single tool, but more like a master recipe for doing really complex science. It's this elegant, structured way of thinking that's designed to tackle exactly these kinds of impossible problems. Okay, so the recipe is built on 6 core steps, or blocks, and you always follow them in this order. You kick things off with monster harvest, which is just a great name for gathering up all your raw data. Then you set up your experiment in cube design, process it with the label engine, and then check the quality with a gate. Finally, you figure out any uncertainty with UQ, and you wrap it all up in the artifact. This 6-step structure, it never ever changes. It provides a common language for all kinds of complex science. And this is where you can really see the genius of this thing. While that 6-block skeleton is totally fixed, the ingredients, the actual methods you use inside each block, are completely flexible. They're called plugins. It's like having a master recipe for a cake, right? The steps are always the same, but you get to choose whether you use butter or oil, chocolate or vanilla, and you control it all just by changing a single file. Let's make that a little more real. Take a look at block 2, cube design. This is where you set up your whole experiment. You've got choices. For generating your test data, do you want to use the Sobel engine, which samples points really evenly? Or maybe the LHS engine, which is more of a random approach? For dealing with categories, do you use one-hot encoding or target underscore encode? These are all just different ways to turn concepts into numbers the model can understand. You just pick the best tool for your specific question, which makes the whole framework incredibly powerful and adaptable. So, with this amazing recipe in hand, how did researchers actually apply it back to our original problem, those impossibly complex spinning black holes? Well, their goal was to build something called a surrogate model. And a surrogate model is, well, it's exactly what it sounds like. It's a stand-in. When the real physics is just too difficult or slow to calculate directly, you build a really accurate statistical model that approximates the behavior of that system. It's a super clever way to get reliable answers without having to solve those impossible equations. So here are the actual ingredients they chose for their black hole recipe. In block 1, you can't just go out and measure a higher dimensional black hole, right? So they used a synthetic data source, generating 50,000 perfect numerical solutions to learn from. Then, down at the gate in block 4, they set a simple rule: only accept variables that had a really strong correlation. This just makes sure the model is built on solid ground. Now, here's the best part. Following this structured, rigorous recipe didn't just work. It led to some absolutely incredible breakthroughs. It let scientists see things about these black holes that were totally hidden before, just buried in all that mathematical complexity. So, you might be wondering, just how accurate was this surrogate model? Get this. The R-squared value, which is basically a score for its predictive power, was 0.998. That is just staggeringly accurate. It means their statistical stand-in was able to predict a key physical property with near-perfect precision, all without ever solving the full impossible equations. And this accuracy led to a really profound insight, which is summed up in this quote from the research. What they figured out is that the very shape of the data, what they call the phase space topology, actually holds the secrets to the black hole's stability. Essentially, the model found this brilliant shortcut. It could tell if a black hole was stable or not without having to do all the brutal, complex calculations that were required before. And the breakthroughs just kept on coming. Using this model, they could finally pinpoint the exact speed where these black holes spin themselves into instability. They could even estimate the effects of an infinite number of tiny physical factors, a task that is just mathematically mind-boggling. I mean, they were finally answering questions that had been completely out of reach for decades. This chart really drives the point home. It shows just how accurate the model was at predicting some really complex physics across different dimensions of space-time. I mean, look at that. Even in 9 dimensions, the accuracy is almost 97%. The recipe was just consistently powerful, no matter how complex the problem got. So this is so much bigger than just black holes. What we're really looking at here is a universal tool for discovery. By creating this common framework, the MPP recipe makes complex science more reproducible, more transparent, and more collaborative. Scientists don't have to reinvent the wheel every single time. They can just pick new ingredients for the recipe. We started with its origin story, right? Probing the fundamental nature of gravity by modeling the stability of these exotic black holes, a truly foundational problem in physics. But then, and this is the really amazing part, researchers applied the exact same 6-block recipe to a totally different problem, modeling how much carbon is captured by trees in Metro Manila. They just swapped the synthetic data plugin for one that uses satellite images and measurements on the ground, all for the really practical goal of creating carbon credits. And they didn't stop there. The recipe has also been used for climate engineering, analyzing the energy costs of plants designed to capture CO2 directly from the air. In this case, the plugins were all about engineering specs and efficiency data. So you've got astrophysics, urban ecology, and climate tech. And the same fundamental recipe works for all of them. And that really leaves us with a fascinating final thought. If we actually have a universal recipe for making progress on science's hardest challenges, the only question left is, what impossible problem should we solve next? A framework like this doesn't just solve problems. It really changes how we think about discovery itself.